Well, recall what we defined our Lagrangian to be. It's this constant b times ds over dt, which, ignoring time dependence, we want to ignore time dependence and only functions of x and x dots. I'm going to rewrite that. Alright. Now I'm going to write these metric components as in terms of fluctuations. Are we're going to, as fluctuations around the flat space interval. And that's a function of the coordinates, c squared times 1 plus that, and as the fluctuation vanishes, you just get flat space. I'll say psi i. Write that down. That was bad. We've defined our Lagrangian as this. I'm going to divide out the factor of c. BC, AD. Now, in the situation where our velocities are way less than the speed of light, which is almost every single practical circumstance, that's going to be a very, very tiny number, very redundant. And this little fluctuation in the spatial metric components is going to be even smaller, compared to that factor of 1. So we're going to ignore that, and we're just going to consider our Lagrangian to be equal to BC 1 plus, if I call that psi, I know that's, here, I'm just going to rename that to psi, minus sum over I squared over c squared. When you perform the sum over x dot I squared, we're just going to say that that is the magnitude of the velocity vector, so when in our case, that means that the energy equals summed over I minus L. We're gonna look at the no, hold on a second. When you take the derivative with respect to one of the x dot i's, it'll be 1 over 2, 1 plus v squared over c squared, 2 xi over c squared, xi squared, minus, bc that's just going to become an x dot I squared. I'm having trouble. I've gone lower on the page and I'm looking at my camera and not my actual paper. That factor of 2 will cancel. And then when you sum over I, that'll just give us our v squared over c squared again. So this is just E equals negative BC. Pull out that factor of 1 plus psi minus v squared over c squared. e squared over c squared plus, and when you pull that out, that'll just square that, so it'll just be 1 plus psi minus v squared over c squared. And get E equals negative bc. Well, let's consider that we strip away all of the motion and all of the what will be interpreted as external forces, which removes the fluctuation psi, and you'll just get E equals, and it's basically the energy of the self energy, the rest energy of the particle itself. So that's what we're going to define that as. We're going to define this as the rest energy. So B, we're going to define, it's kind of redundant, but to show, the approximate reduction to classical physics. E 0 over C. Rest energy over C. Okay, I need a paperweight. And as we consider the limit that the velocities v squared over c squared is way less than 1, and that psi, the fluctuation, is fairly small, as we consider that limit, negative bc plus psi that's that. This is just, let's rewrite this over here. BC 1 plus psi to negative 1/2 power. Now that's a very small number, and 1 plus u negative 1/2 is approximately minus 1/2 u. So we'll do negative BC 1 plus E is approximately equal to 1 plus psi 1/2 psi plus v squared over 2c squared. BC 1 plus psi, and 1 plus A, 1 plus B, when A and B are very small, it's just approximately 1 plus A plus B, because all the AB terms vanish away. So 1/2 psi plus v squared over 2c squared. I don't know why I'm using BC when I said E sub 0. That's just the rest energy. E sub 0 psi and E sub 0 2c squared. So E is E sub 0 plus 1/2 E sub 0 psi plus, now that's our energy. Now if you strip away the self energy, the rest energy, and you strip away all the energy due to motion, you're left with this, and we call this the potential energy. And then you take away the rest energy and the potential energy, and you're left with parts that are specifically due to velocity and motion, and we call this kinetic energy. Well, let's look at our Lagrangian. Using BC properly. dt 1 plus psi. We don't need this. That's the action, not the Lagrangian. Yeah, let's go ahead and do our action. Our action principle. When these are very small, are 1 plus 1/2 psi minus v squared over 2c squared is roughly equal to our action. Well, this part just goes to negative dt EO squared over 2c squared minus EO2. Well, this is just going to be integrate, because that's a constant. It's going to be our change in time times E sub 0. That's going to be redundant in most of our calculations because it doesn't vary anything. It's not going to play into our equations of motion. So we're going to ignore this part. Action is approximately equal to this. Well, as we define, that's just our kinetic energy. And this was the form of our potential energy, so that's -1 times our potential energy. So our action, so this is kind of the program of standard physics. And the idea is that the curvature what made it indistinguishable from external forces. Loosely, it's not entirely exact, but again, this whole thing was just a demonstration, a rough demonstration. So the program of classical physics is basically that you have a kinetic energy minus a potential energy, you integrate over time, and that's our action. And that our action, our path chosen is the one which minimizes this action. We call this kinetic minus potential, the Lagrangian. And that will give us our Euler-Lagrange equations. And that's kind of how, from relativity, the principles, the idea of classical mechanics isn't so far-fetched. When I originally was going to make this video, I had a hard time explaining, as I said, the Lagrangian, like why is the Lagrangian kinetic minus potential? It just seemed kind of hard to just start to explain out of the blue, so I did the unintuitive thing and did a rough, inexact sketch of why the math works out that way from more complicated principles. Well, not really more complicated, but more what's usually considered more advanced principles. I think they're more fundamental ones, but